if you call, let's do one, for example, let's use a converging lens. If you place your object at a distance, I'm going to call it SO for object, then the image of the object is going to be at some place. If this is a converging lens and the focal point is, say, over here, then we know that the image is going to be somewhere on this side and it's going to be inverted. And that image is going to be at a distance from the lens that I'm going to call SI, distance of the image. That's the object, that's the image. The convention is to call the distance of the image positive if, in the case of a converging lens, if it's on the right side of the lens, that is, on the side of the lens towards the direction in which the light rays are propagating. So if this is the object, the light rays that we're interested in are moving that way, and the observer must be somewhere here. Okay, that's important. So you can call that the downstream direction. And when the image of the object is located on the downstream side of the lens, then I'm going to call that positive. The other important thing to keep in mind when using this equation, which is pretty simple to use, is that the focal length can be a positive or negative number depending on whether the object is converging or diverging. If it's a converging lens, then you use a positive number for that distance. If it's diverging, you put a minus sign. The same for mirrors. If it's a concave mirror, you're going to use a positive focal length. If it's a convex mirror, you're going to use a negative. Okay? Remember the analogy between concave and converging and convex and diverging. They follow the same rules for the focal length. So F can be positive or F can be negative for converging, either lens or mirror, and negative for diverging, either lens or mirror. So that tells you the convention for F. Very important. I just told you the convention for the distance to the image. There is also a convention for the distance to the object. And it can also be positive or negative. Your book doesn't discuss that. It leaves that out. But when you're combining lenses, whenever you have a problem where you're going to combine lenses, when you have more than one lens, there will be cases you have to, a textbook has to struggle to find only the cases where in all the calculation you're using distance of objects positive. That's what the book did, but I don't think that's a very good idea. Because you will find problems where that's not the case and you will be lost. You will not know what to do. You will get the wrong answer. You will know what to do, but it will be wrong. So the convention for the distance to the object is that it is positive if the object is upstream from the optical element, and since what I'm saying applies to both lenses and mirrors, I'm not going to say lens or mirror, I'm just going to call it from the optical element. The optical element. That's what this means. So the distance to the object is going to be positive if the object is upstream, but the distance could be negative if the object is downstream. And I'll show you when you can have this case. So that's for the object. For the image, again, positive if the image is downstream, not upstream, but downstream. From the optical element. You will be wondering in some problems, downstream from what? From the observer, downstream from the object? The answer is downstream from the lens or the mirror. You have to stand at the lens or mirror location and say, where is my downstream direction? Where is my upstream direction? Do I find the image downstream? Yes, then that distance to the image is positive. Do I find the image in the upstream direction? Then that distance is going to be negative. Okay, we'll do a few examples with that. And it is negative when the image is upstream from the optical element. So you need to remember that convention for how to handle the signs for the quantities that you find in the thin lens equation. If you get one of those signs wrong, then of course the answer will be wrong. Let's start looking at that and how you use the thin lens equation in particular situations. So let's take a converging lens, focal length f, and let's assume that you put your object here at a distance that is 2f. The question is, where is the image? You already know that because this is a converging lens and you're further than the focal length, the image is going to be inverted on the other side, right? But you don't know exactly where. You could do your ray tracing, draw this using a scale and find that, but it obviously is much easier to just use an equation and plug in a number and find the answer. So let's do that. The equation says that 1 over f equals 1 over the distance to the object plus 1 over the distance to the image. And we're looking for this. And I didn't give you any numbers. So 1 over f is the focal length of this, and there's a positive sign there because it's converging lens. And the distance to the object seems to be 2f. And this is going to be the distance to the image. So I solve for this. So 1 over s prime is equal to 1 over f minus 1 over 2f. So this is 1 over f, and that 1 minus a half is a half. So that tells you that the distance to the image is going to be 2f. Right? I just inverted that, and I get 2f. So if you're at 2f, you actually form an image also at 2f. Somewhere here. Now what can you say about the size of that image? How much bigger is the image with respect to the object? Bigger, smaller, same size? Is it bigger? How do we know? So this distance over here is 2f. And notice that our answer is a positive number, right? Which agrees with the convention that we're using. Positive distance for the image. Positive distance for the image means that the image is downstream. The downstream direction for this problem is that. When you're standing here at the location of the lens, the downstream is that way. And that's where you find the image that is positive 2 2f. Okay? If you had gotten minus 2f, then the image will have been on this side. Okay? So, but back to the question about the size. This distance is 2f, this distance is 2f. This angle, that I'm going to call alpha, how does it relate to beta? Should be the same, right? Because it's just one is the angle formed between the horizontal and a line that crosses the horizontal at some angle. That's basic properties, basic geometry, right? So those angles have to be the same. So if those angles are the same and these distances are the same, what can I say about this? It has to be the same. So the height of the image is going to be equal to the height of the object. Except that if I want to keep track of whether the image is upright or inverted, maybe I should put in a minus sign there to indicate that the image is inverted, right? This could be the location of the tip. That equation could mean the location of the tip. So if the location of the tip on the object is positive, the location of the tip on the image is going to be negative, right? Because those angles are the same, what determines the relative size of the image and the object is just what's the ratio of the distances, right? Which is the magnification equation. It tells you how much bigger is the image going to be with respect to the object. If the image is far away from the lens, this equation tells you that the magnification is going to be bigger than 1, right? Because you know that the image is going to be along this line. So if the distance is very big, the size of this arrow is going to have to be very big also to match that, right? That is simply coming from the tangent of this angle is this divided by that, which should be the same as this divided by that, right? The tangent of that angle alpha shown there is the height of the object divided by the distance of the object, and that angle is the same on the other side, so it's equal to the size of the image divided by the distance of the image, which means that the ratio between the size of the image and the size of the object, if you take this divided by that, you bring the other one over there, is the ratio, the same as the ratio between the distances of the image and the object. And for the magnification, I put a minus sign there because I know that when the S is positive, when the distance to the image is positive, the object is going to be inverted. The image is going to be inverted, right? So if I want to have the information about that, then I will put a minus sign there to indicate that when SI is positive, the magnification is negative, meaning inverted. All right? What if I put now the object at a distance that is f divided by 2? Same converging lens as before. Where is the image of that object? You already should have an idea of where you're going to find that from ray tracing and what we said before. But let's do the equation. 1 over f is the focal length of the lens. Should be 1 over the distance to the object, right? The object is emitting light this way, which is going through the lens that way. So again, that's the downstream, that's the upstream direction. We're in the upstream direction, so the distance of the object is going to be positive. It's going to be f divided by 2. And we're looking for the distance of the image. So the distance of the image, 1 over SI, is equal to 1 over F, and I'm going to bring this to the left side with a minus. Minus, the 2 goes up on top. Okay, so what is the answer finally for the distance to the image? Minus F, right? 1 over F, factor of 1 minus 2, that's minus 1. Flip it, minus F. So if you put your object here, halfway between the focal point and the mirror, the image is going to be formed back here. The answer for the distance of the image is negative, right? Does that coincide with what how we define the downstream and upstream? If you're standing at the lens, the downstream direction is this. The light rays are going that way. The light rays are not going that way, right? The observer is here, and the observer sees these diverging light rays, and they seem to be coming from that point, and that's where the observer thinks that the image is. So if you're standing here, which is where you're always standing when you decide downstream or upstream, the image can be found in the upstream direction. That is consistent with this minus sign here. Okay? So when you get your answer minus F, and then the next question is draw the image, right? You have to think about this. This means upstream from the lens. That means the image is going to be over here, not over there. All right? This is very important because this image, I said when you have more than one lens, it's going to be important to figure out that, because then in the calculation with several lenses, you're just going to take this answer and stick it in the next equation, right? Crank it and get the final answer. But you have to think about these things. You might have to flip the sign depending on where the other lens is and so on. How big is that image compared to the object? How much bigger? Factor of 2, right? The magnification will be minus SI divided by SO. SI we found that is minus F, and SO was F divided by 2. So that gives you minus with minus plus 2. So 2 times as big, that's a magnifying glass, the way you're using it. What about for a mirror? If it's a concave mirror like this one, the focal length is going to be a positive number, so I'm just going to call it F. And to find the location, if this is the object, to find the location of the image, you go back to the same equation. It's called the thin lens equation, but it applies to mirrors also. So 1 over F equals 1 over the distance to the object plus 1 over the distance to the image. As I said, this is a positive number for a concave mirror. Distance to the object, in this example, is 2f. And we're solving for the distance to the image. So that is 1 minus a half, that's 1/2. And f is over here. Right? So the distance of where the image is located is a distance 2f from the mirror. Now notice that you got a positive number there. Where do I draw it? Is it behind the mirror or is it in front of the mirror? From the ray tracing that we've done for this kind of mirror, you already know that it's going to be inverted because the distance from the lens is bigger than one focal length, right? And so it's going to be inverted. And it's going to be on this side, it's going to be real image. Right? So what I want you to notice is how do we reconcile that with what we said about the distances of the objects and the distances of the images, distance of the image in particular. So the image is, according to that, the image is downstream, correct? Because we got a positive number over there, the image is downstream. Downstream for a mirror, it's actually, so think of the light rays as a stream of water, for example, hits the mirror and it bounces back that way. So it's like a bending in a river. Right? The river comes in one direction and it bends and it turns around 180 degrees. This is still the downstream direction for the image. So an image that is located on that side, that is the downstream direction for the image as you're located on the mirror. So that is a positive distance to the image. Okay? And the object was in the upstream direction. If you're standing here for an object, the upstream direction is to find the object, you will have to go upstream this way. So that would be also a positive number. Okay? So that's a source of confusion there, because that is the one difference that you have between the lenses and the mirrors. Yeah? Can you speak up? Exactly. That's right. So you always have to consider, for the image, you have to consider that the light rays must have already interacted with the optical element.